Babbage and his engines, part 4, the analytical engine. This machine has never been built. If it had been, it would look somewhat like this in Sidney Paget's cartoon. Absolutely enormous, about the size of a locomotive engine. And Babbage had separated the memory store from the place where calculations took part. And you can see the store on the left behind Babbage. It goes on forever. And on the right, in front of Ada, is the mill. The mill was where all the processing took place. Numbers were retrieved from the store into the mill, calculations occurred, and answers stored back there. The instructions for the machine and the data all came in through punch cards. The machine, of course, had a printer. These points here are modern terms that will be used on a modern computer. I'm not going to go through them because Babbage wouldn't have understood them either. They're just there because you show the sophistication of this machine. It was indeed a computer. What does that mean when we say a computer? Well, in the first talk, I stayed away from things like the abacus. Incredibly useful device, but you have to know how arithmetic works. You have to know how the carries work before you can use it successfully. The prototype of the difference engine, shown top center, is the first machine in which you could put numbers in by turning the wheels, pull the crank at the top, and the addition would take place entirely automatically, including the carries. In the computer, it's a bit different. And I think Adrian Johnson at Royal Holloway put it very well. He said, think of a mid-century record player. He said you could look at the thing, if you'd never seen one before, and soon realize that the vinyl disc would rotate and it had a groove in it. The groove had little wiggles, and there was an arm with a needle, and the needle would follow those wiggles. If you took it apart and looked inside, you could see a pickup coil that made an electric current from the wiggling of the needle. And you'd find vacuum tubes, valves inside that would amplify that signal and drive the cone of a loudspeaker in and out in proportion to the wiggles in the record. You could change the record. You could play a Mozart sonata, or you could play the latest Rolling Stones hit. Wouldn't matter. The machine does exactly the same thing every time. It just methodically follows that groove and produces the motion in a larger scale in the loudspeaker. The computer on the left is quite different. You could take it apart, look at every component inside, trace every connection between every transistor in the integrated circuits, and you would not be able to predict what the machine did and what would appear on the screen. Because you've only got half of it there. It won't do anything until you put the program in. And the program tells the machine not only what to do, but to a great extent, how to do it. And Babbage was the first individual to work with systems where the function transcends the components. In Babbage's plan view here, we see on the right the memory store going off, and the circular section on the left is the mill where the calculations take place. It's very difficult to find out just how this machine works. After all, nobody has ever built it, so there's nothing to go and see, and there are no websites that have nice animations of the thing in operation. The primary source would be Babbage's papers, which is in the archive at the Science Museum. They've been digitized and they're available on the web. The trouble is, there are about 700 engineering drawings, roughly 3 feet by 4 feet, about 1,000 sketches, and about 20,000 notebook pages. It's totally intimidating. And the Science Museum had done a great job recently in at least putting labels and descriptions on these drawings. And you can go in and download something. I did this here. It's actually a very clear drawing if you have a large enough screen, and you haven't compressed it for zoom. The problem is that there's an overview in the top left, and there are hundreds of these detailed drawings. And there's no linkage between them. There are no sub-assemblies, no diagrams showing how things fit together. So it's details are there. It's very difficult to get a handle on the machine. Menabre's lecture, which was translated by Ada Lovelace, describes the operation of the machine in theoretical terms, technical terms. It doesn't contain any nice illustrations. For that, we have to go to Ellen Bromley, the professor of computer science from Sydney, Australia, who spent a year's sabbatical at a science museum going through Babbage's papers, particularly related to the analytical engine. He published this paper in the Annals of the History of Computing, and it contains some very nice diagrams. Now, he does preface these by saying they are simplifications. The other source that's readily accessible is his book, published by Sidney Padua, Canadian graphics artist, Thrilling Adventures of Lovelace and Babbage. Don't be put off by the fact that it's a graphic novel. The first part of the book is a series of cartoons of Ada and Charles's life and times. They are about the same length of Ada's translation of Menabre's paper, and Sidney Padua's footnotes are about the same length of Ada Lovelace's footnotes of her translation. And it's the footnotes that contain an incredible amount of historical detail. And I've drawn on those quite freely in these talks. The engine itself, you see on the right in blue, the memory, two banks of memory. Each bank had 50 numbers, each number having 50 digits. And on the left, there's the mill. There's an egress and ingress registers, and they are sort of intermediate stages between the memory store and the place where the addition and other calculations take place. The red rectangle covers a section of the memory store of two memory locations. And I made a model of that part of the store. And just below it is a picture of a card reader that will be used to read in data cards. This is the model I made. It's 3D printed, and it contains two 3-digit numbers. I'm going to use this model to demonstrate how the memory part of the machine worked, and then we'll use some other diagrams to go through the arithmetic. The core of the memory is this figure wheel, about 1.5 inches across and about 4 centimeters. This part of the machine and these diagrams are in the style of Babbage's design and about the same size, but they're not historically correct. These parts were 3D printed. It's easy to make some things on a 3D printer that are difficult to make out of metal, and vice versa. So I used a compromise here. Now these figure wheels, and remember there's two banks of 50 of them, 50 numbers, and there are 50 digits going up vertically. So this is just the units section of one of those memory locations. In the left, there's a green rack. A rack is just a rectangular bar with gear teeth on it. And the brown section to the left of the figure wheel is a linkage pinion, and it's free to rotate, and it on a shaft, and it can be raised and lowered. In the down position here, the rack can move in and out and does absolutely nothing to this figure wheel. But if we lift the pinion up, then as the rack moves in, it turns the figure wheel via the motion of the pinion. And the rack, out on the far right of the picture here, is connected to the card reader. All data has to come from cards. A card is read, and the pinion links the rack to the figure wheel in which the number is to be stored. That's one of the 50 figure wheels across. And the number read from the card is stored in the figure wheel. So if a digit 1 is read, then the rack doesn't move very far. If a digit 9 is read, then the rack moves a lot farther. So we get 9 stored into the figure wheel. To get a number out, or to return the figure wheel to 0, the linkage pinion is dropped down, and then this green section in the center of the figure wheel is a drum with a little tab at the back, and that tab engages on an indent inside the figure wheel. And as it goes from the 9 position, which is its home position, this is the green part, and it goes anti-clockwise, going back to the 0 position, it will at some point pick up the indent inside the figure wheel and turn the figure wheel to its 0 position. And that does nothing at all to the rack. It just brings the number back to 0, clears the memory. On the other hand, if the pinion had been raised and the rod here that holds that green bar system returns to 0, then the pinion will transfer the data into the rack, and the rack will be pushed out to the right by the same distance it was pushed in when the data was originally read. This is just a close-up. It shows how blah, blah, blah. This is just a close-up. It shows how the vertical shaft, which is linked to the green arm, rotates the green arm from the 9 to the 0 position, and on the way picks up the indent inside the figure wheel, returning the figure wheel to 0 and giving off the number that was stored there. To make that work, the vertical rod that holds those arms goes right up to the top of the machine. You just see the units here, but the tens, hundreds, etc. are up above. And it extends into the basement, what I call the basement, where there's a control system. And that control gear has its own pinion and its own rack. So when the control rack moves across, right to left, it will turn its pinion, it will rotate the gear wheel, and that will rotate all the green arms above inside the figure wheels, returning all the figure wheels above to their 0 position. This is the model here, and you see units, tens, and hundreds. And the blue sections are sections that are done in the style of Babbage and about the same size. And the control section underneath, likewise, is similar to Babbage's design. Now, I don't have a card reader. I didn't print one. So I faked it out. I used 3 stepper motors, pretending to be the card reader. A stepper motor is a small electric motor, well, small in my case, and it will return in either direction, and it can be stopped anywhere. And if you want to see one in operation, just watch your washing machine. In the wash cycle, it will turn the drum clockwise and anti-clockwise, stopping now and again to wash the clothes, and later on it will spin very fast to spin them dry. Another stepping motor is moved down here to drive the control rack in and out. In Babbage's day, that would have been operated and linked from the steam engine. Underneath that, Babbage would have had a whole mass of cams and gears and linkage shafts to make these linkage pinions go up and down. Again, I took a bit of a cheating here. I used the servo motors. These are small, in my case, small electric motors that will move an arm between 0 degrees and 180 degrees and stop anywhere along that path. I can say stop at 40 degrees or stop at 72 degrees with instructions from a computer. If you want to see one of these in motion, just take a cruise. The rudder on the boat will be a sort of a large version of my servo motors. 90 degrees will be straight ahead. And underneath here is the electronics. I have three microcontrollers. One controls the system, and there are two peripherals that control the mechanism of the servo motors and the stepper motors. And they're in a network. Here's a close-up view of just the section that holds the digits and the control at the bottom. And at the top on the left are three racks, units, tens, and hundreds. And at the bottom left is the control rack. Here's a side view, seeing the racks, and you can see the pinions that they're in the down position, not linking to the racks. On the right, this is a close-up of a gear attached to the stepper motor below, and it's linked into the rack. And this is the same setup, excuse me, for both the control and the three data racks, units, tens, hundreds. Here's an overview of the whole system. It stands about 18 inches high, about half a meter. And we can see it in operation, storing a 3-digit number. The first step is to move over the control rack, reducing all the numbers above to 0. Has to be done before you can store new numbers. Now the data racks are going across to the right, ready to pick up the numbers from the punch card. Here they come in, different distances because of different numbers. And now the control racks are going to their home position. We can watch that in close up, and this just shows the 3 digits. The racks are getting set up. The control rack is zeroing the numbers. The data racks are going across to the right, ready to pick up the card data. And now the numbers are being stored. And everything's now going home. To get a number out, that blue arm inside the figure wheel goes from the 9 to the 0 position, brings the figure wheel back to 0, and the motion is transferred through the pinion into the rack. But the problem is that leaves the figure wheel at 0. We've lost the number that was already there. Babbage solved that problem by setting up a reserve wheel. It's a mirror image of the figure wheel, and it hangs upside down over the figure wheel. And there's an additional pinion gear here. And as the figure wheel is returned to its 0 position, the motion is transferred up through this gear into the reserve wheel. So when the motion has finished, i.e. the figure wheel is back at 0 and the rack is moved out where it should be, then that linkage pinion on the left is dropped down, and the green arm inside the figure wheel lifts up, so it's inside the reserve wheel. And then the control rack does its thing and returns that green lever inside the now reserve wheel from its 0 position to its home position at 9. And as it does so, it returns the reserve wheel to 0, transferring its data through that funny gear on the right down into the figure wheel. And because the figure wheel isn't connected to the rack at the back, it doesn't do anything there at all. It just brings it back to its original value. We can see that working here. You can see at the bottom the control layer, and above that the figure wheel, and above that the reserve wheel. Doing the setup, putting the number 8 into the reserve, and now returning it to the figure wheel. And I'll show that again. Data and instructions came in from punch cards. These are punch cards with a Jacquard loom. No card analytical engine because nobody built it. The difference from 20th century cards is that all the holes are punched out except the ones that are needed. And the holes on the right and left-hand side are so the cards could be strung together with string and not get out of place. The reason for punching out everything except the ones you wanted is because the punch card was pressed up against a bank of rods. And you only wanted to move the rod of the number, or digit, I should say. You only needed to move the rod for the digits you wanted to say. So most of the rods would remain in their home position when the card was pushed forward. Some of the rods would be pushed back, and they would engage with a pinion that would be linked to a rack that would be linked in turn to a figure wheel, as we saw earlier. This is grossly oversimplified because the rod for the digit 1 can't move the pinion very far. The rod for digit 9 had to move it a long way. And of course, every hole in the punch card needed a little pinion to do that, and the whole thing had to be linked together. Another problem was that the punch card, the paste card, wouldn't have enough strength to push in one of these rods to make all this motion happen. And remember, those figure wheels could be 30 feet away, and they could be right up at the top on a back pile of 50 of these. So all sorts of linkages that would take a lot of force to move. And there are consequences of this. See, before a number can be stored, the pinion linking the rack to the figure wheel must be raised and in place. And before that, the card reader must be connected to the correct memory bank. And before that, we must know that we want to store a number from a card from memory. That means that Babbage had to build 3 card readers, each with a different card in. The first card reader would have read in the instruction card to say, we're going to store a number. The second card would say which memory location was that going to be stored, and that would set up the pinion to link the rack to the correct figure wheel. And finally, the third card reader would have the actual number that we wanted to store. You see, it's in a mechanical system, and there's no opportunity to buffer information. If you read a card, the information must be stored immediately, so all the linkages must be in place to make it happen. And here's just a larger diagram, again, grossly simplified. And again, there are 50 figure wheels vertically and 50 numbers horizontally, and a second bank behind this one for the other 50 figure wheels. Now, this is one of Sydney's Padua's cartoons. It shows a very simplified punch card with only one hole in it. And when the punch card is moved forward to the right, of course, the hole just goes over that horizontal rod and doesn't do anything, which is absolutely fine. That's what we want. However, if there's no hole, then it pushes that horizontal bar to the right, swings that vertical arm, which pulls out to the left a piece of metal that's locking that vertical rod. The vertical rod has steam pressure under it. So when the punch card is advanced and the little block of metal at the bottom pulls out of the slot, then the rod moves up and the gear engages between the pinion and the figure wheel above. That's the way that a small amount of force from the punch card can hook up some gearing that will transmit a large amount of force through steam power. And I'm going into this picayune detail on purpose. And in the diagram that Babbage had, this particular card reader of his number card would read 44 numbers with a potential of holes 1 through 9 to be left intact. You didn't need to do anything with 0 because 0 didn't do anything at all. You didn't need a hole for it. But anyway, you've got 44 numbers, each with 9 possible holes. And that means there are 396 possible holes, and each hole needs this mechanism shown on the left. So there are 4 moving parts for every hole, which means it takes 1,584 moving parts, plus the supporting systems, to get the data off the card. That's before you put the number into memory and before you get the number out of memory and do something with it. There's absolutely no way anybody in Victorian times or even today would consider building this mechanically. The money to take them to do it today, well, I can think of better things to spend it on, sorry. Here's a view, but standing back. We see a number being read off from the memory, given off to a rack. The rack moves to the left, and at the bottom left here, there's this large wheel. It's about 1 meter diameter, about 3 feet diameter, give or take. And yes, there's another pinion that lifts up, and it engages the rack with this big wheel. And so when the number is read off, it moves the rack to the left, rotates the wheel, and rotates the big gear underneath. And again, there are 50 of these gears going up. So the wheel rotates by the distance depending on the number. And around the wheel, there are other pinions that come up so that it can be linked to other parts of the mill. So that way, a number can be given off by a figure wheel, transferred through the rack to this big circular gear, and that in turn transferred to some part of the mill. So how do we do addition? Well, here we see the diagram again. And we first read a number off of a memory store and take it into the ingress register. That's done because the card, instruction card, could say, get the number from this particular memory location, or get the card from the card reader. Putting it into the ingress register means the rest of the system doesn't have to know where the card came from. And once it's in there, it's transferred through that big wheel into the lower part of the accumulator. The second number is retrieved, and again, it could come from memory or from a punch card, and is put in the upper part of the accumulator. And then the upper part accumulator is added into the lower, and the result stored back into the egress register. And from the egress register, it can be stored in the memory location, it could be punched out to a card punch, or it could go to the printer, or it could go to the plotter. Multiplication, well, it starts to get interesting here. Again, the first number is retrieved, either from memory or a punch card, and is put into the upper accumulator. That is added into the lower accumulator, which was previously set to 0. So now the lower accumulator contains 1 times the number, and it is stored in a special T1 register. The addition is repeated, and it's now 2 times the number, and that's stored in the T2 register. So you can see what's going to happen. We're building up a times table in T1, T2, all the way up to T9. It's easier to explain it now in this form. So I'm going to multiply 27 by 31. So we first build a multiplication table in T1 to T9, a multiplication table of the first number, 27. So there we see it on the right, 27, 54, 81, etc. We then fetch the second number, 31, and we put it into a special register. We take the units digit of 31, which happens to be 1, and add from its table T1, containing 27, and we add that into the output, again, originally set to 0. And then we shift all the T tables up by 1. So we've multiplied by 10. So we now contain 270, 540, etc. And shifting up by 10 is quite easy. All you have to do is move the number in the figure wheel into the number above. And then we go back and repeat step 3. But instead of taking the units position 1, we take the tens position 3. And then we go to the T3 register, which now contains 810, and we add it into the output, giving us 837, which is the answer. And then we save the answer back into the store, the printer, stereotype card, or the plotter. Now, in this setup, if we want to multiply 27 by 31,456, then making up the times table of 27 will require 9 operations. Doing the multiplication by a 5-digit number will need 5 operations, adding in each digit from the corresponding T table. If we reverse the calculation, the times table of 31,456 would still only require 9 operations, but the multiplication will only take 2 operations because we've only got 2 digits. So Babbage, being Babbage, of course, before multiplying the numbers together, moved them into temporary registers. And he had gears and levers and such like to figure out which was the largest, I should say longest number, and rearrange the arithmetic so the multiplication tables were built from the longest number, thus reducing the speed of operation. By Babbage estimate, a multiplication would take about 2.5 minutes. Handling of negative numbers was done by putting an extra figure wheel at the top of each memory column for the sign. Even numbers up there meant that the number below was positive. An odd number meant the number below was negative. The logic of that is that if he was doing multiplication or division, all he had to do was add together the 2 numbers at the top, the 2 sign numbers, because an even plus an even is even, which is the same as multiplying 2 positive numbers, and so on with odd, odd, and even, and the same for division. And he had the mechanism already for adding together 2 numbers, and he didn't need to worry about any carries here. Didn't matter. How did he handle subtraction? He used tens complement. 100 minus 7 is 100 minus 10 plus 3. He has a mechanism for adding, so the adding than 3 is already there. Subtracting 10, well, I think what he would have done, he had a carry mechanism that would bump the number above by 10 if it's a carry from an addition. But if there's a subtraction, he'd have to bump the number above down by 10, which is 1 notch, of course. And I think that's how he would have done it. Now, with division, he used a method of successive subtractions. I don't know how that works. Logic operations, less than, greater than, equal, or equal to 0, were carried out in special registers in the mill. The 2 numbers were put into the registers, and various levers and rods were set depending upon those situations. And looping and branching in the instructions was handled by advancing or retreating the punch cards. I think you could only move 9 at a time, backwards or forwards. So if you wanted to move forward by 12, you'd move forward by 9, and then a second operation to move forward by 3. Now, this means there's an incredible amount of work taking place. If you wanted to multiply 2 numbers together, you have to go through dozens, if not hundreds, of operations to get all of these things set up and working and synchronized. Babbage had a brilliant idea. What he did was go to the barrel organ, and in the barrel organ there's a drum that rotates, and pegs in the drum open and close valves sending compressed air from the bellows up into the organ pipes. He took that idea, put the barrel organ's drum vertically in an arrangement like this, and he set it up so that the drum could be retreated to the right, advanced one face, and then moved back to the left. When it goes back to the left, there are lots of little tabs that are screwed onto the side of the drum, and those little blocks push the various arms in and out. And these arms would go through all sorts of linkages throughout the machine to make those linkage pinions go up and down and make other things happen as needed. There are several of these drums set up. There'll be one for doing multiplication, for example. And it would have dozens, 50 or more faces on the drum. And there are, of course, hundreds of these arms coming out, going off to wherever they went. This is not trivial. In a modern computer, we call this microcontrol. The other part of the engine that's really fascinating is the carry mechanism. In the difference engine, the carry mechanism had to be run 30 times because there were 30 digits in that machine. And the carry from the units to the tens, if the tens position was already at 9, it would have to carry up into the hundreds. So it took one operation to add the digits together, the 30 digits. It would take 29 operations to carry the carries right up to the top of the machine. And that was obviously slow. Babbage spent a couple of years puzzling over this, and he eventually came up with a mechanism. This is one of several Alan Bromley's diagrams showing it operating. I looked at this on and off for 2 or 3 weeks, and then it suddenly struck me. It's one of those things that are very difficult when you first look at it, but when you see it, you realize it is absolutely brilliant and, in fact, incredibly simple. I'm not going to bore you with it now. Babbage tried that and in his memoirs. But of course, you can look up Bromley's paper if you want to. Anyway, Babbage came up with this idea after breakfast one morning. Being Babbage, he ran around the city telling everybody how clever and brilliant he was. And he wrote in his memoirs, and this is a Sidney Pedro cartoon based on his memoirs, "The reader may perhaps be curious to know how I spent the rest of the remarkable day. I dined in Park Lane at the house of a friend. Having mentioned my recent success, I remarked that it had produced an exhilaration of the spirits, which not even his excellent champagne could rival. Having thus forgotten science and enjoyed society for 4 or 5 hours, I returned home. About 1 o'clock, I was asleep in my bed, and thus continued for the next 5 hours. I have a suspicion that without the benefit of PowerPoint and an overhead projector, that would have been one of the most boring dinner parties ever held. But anyway, it was brilliant, and it was a brilliant mechanism." So, moving ahead, how to instruct the engine to compute something like this? The problem is that the sine of 33 degrees could be calculated by the engine. One could write a program to go through the arithmetic to doing that. But since it took about 2.5 minutes to do a multiplication, it would be tedious. So he needed something else. So he figured what he'd do when he got the machine working, he'd program it to operate as a difference engine. And then he could produce all the mathematical tables he wanted. And he could produce his output in punch cards. And he could put the punch cards into drawers, like here. And he'd have a drawer for sines, a drawer for cosines, squares, etc., etc. When the program, or the instructions, I should say, required the sign of 33, it would ring a bell. And the operator would be alerted, and a flag would pop up saying it needed a sign. The operator would go and look in a little window, and it would say 33. I'm not making this up. The operator would go to one of the drawers for signs, open it, take out a punch card that would have punched into it the number 33 and the sign of the number. The operator will put that in some sort of a slot on the machine and pull a lever probably. And the machine would, of course, read that and first of all check to see that the operator put in the right number and of course, put in a card for signs. If it didn't, the much larger bell would ring and a much bigger red flag this time would start flapping around and the operator would have to go and fix the mistake. One of the problems Babbage had was the slack in all these linkages, and he had far more linkages than he had in the difference engine, so the slack was far greater and far more problematic. In this diagram, I've just put together 10 gears, each with 20 teeth per gear, and I've suggested a 0.010 tolerance, which is probably typical of handmade parts, and they're probably a lot worse than this in practice after some wear. You have to have tolerances in gears and linkages. If you don't, they'll jam up. There has to be a bit of freedom to play with. So Babbage had to introduce locks, just like he did in a difference engine. But you couldn't apply all three locks at once. The reason is that without the lock, if you advance the gear on the left by 1 notch, the gear on the right wouldn't move, or not enough to register. So he had to put a lock into the gear on the left, and then wait until the motion had migrated down to the center one. And at that point, he could apply a lock in the center one, bringing it back to its correct position. And that would migrate down to the last gear. And that all took time. So Babbage came up with his timing diagrams. And in these diagrams, the vertical bars indicate when things are turned on and off, and the sequence of events. And for each of these locks, he had to have a rod going down the length of the mechanism with cams, off-centered wheels. And as the rod rotated, the cams would be lifted up in the correct sequence to give time for the movement to migrate down the chain of gears. Here are some notes of Babbage's on how instructions would be written to carry out a particular operation. And if you're interested in writing programs for this machine, there's an emulator on the web. There may well be more than one. You can put in an instruction and you can run it, and you can see the memory locations and the parts of the major parts of the mill changing values. Here's a program to compute 500 divided by 30. The comments on the right, past the slashes, are modern, just there for our convenience. And the instructions on the left have been simplified. Thank you very much, it's a good thing. Because the N001 plus 500 in the first instruction means read a card, put it in memory location 1, and the number you have to put in location 1 is of plus 500. And as I explained earlier, we needed 3 card readers and 3 cards to do this. So in the actual engine, the instruction card would say N, the linkage card would say 001, and the data card would say plus 500, and they would be read in sequence as needed. It's obviously far more convenient in the emulator to do that in one line. So after the first line, we got 500 in memory location 1. The second line puts 30 into memory location 2. The slash sets the machine up for divide. The L001 loads the number at location 1 in the store into ingress register axis 1, and the L2 that follows it loads the number at memory location 2 into the second ingress register. So now we've got the 2 numbers in the 2 ingress registers, and that we start that operation using that fancy bit of gear based on the barrel organ drum set vertically. Starts the operation. And when it's finished, the next card here is a P card. It says print the current value on the egress axis, so it's printed out. S003 prime, that little quote thingy there is a prime, stores the primary result of the print on the primed egress axis into memory location 3. The primed result is simply the answer. 7 divided by 3 is 2. The remainder is in the second egress register, and the S004 stores the remainder from a division at memory address 4. The B rings a bell, and the H halts the engine. Babbage came up with something that's about as remarkable as the design of his engines. And it answers the question, how is it one individual working alone could have synthesized a working computer design over quite a short period? Designing an object whose complexity of behavior so far exceeded that of contemporary machines that it would not be matched for over 100 years. And you see below the overview, and on the right, one of the detailed diagrams. And as I said earlier, there was no way of really figuring out how it all worked. And in 1826, he published a paper on a method of expressing by signs the action of machinery. His idea was to take a detailed structure of a machine and abstract a kind of symbolic diagram of how its parts act on each other. His first example was a hydraulic device. His second example was the way a clock works. These are the gears on the clock and the operation of their motion. He applied this partly to the difference engine, but most significantly to the analytical engine. And this is just one part of one of his many diagrams. It's completely incomprehensible for mere mortals. He didn't write a user guide. There is a pamphlet that he printed for the Great Exhibition of 1851, but it's such a summary level that, well, that doesn't make much sense, really. Now, greater minds than mine have spent a lot of time recently going through this symbolic notation and have started to figure it out. And the close-up here, I think the big letters, the K's and the R's and so on, use 4 different alphabets for this. They are representing parts of the machine. And then the little symbols above and below the letters, and they could be top left, center, or top right, bottom left, center, or bottom right. They will indicate certain things about the action. And the arrows and the lowercase letters mean things happening. And they can be linear motions, smooth rotary motions, or stepping operations. Nothing like this was seen for another 100 years. And this is just part of a layout of how today people lay out the operation of circuit diagrams inside chips, silicon chips, which have thousands and thousands of, or millions and billions today, of logic operations. And here, the logic operations, the and, ors, etc., are represented by symbols of binary arithmetic. And these symbols were developed by Boole, who was a colleague of Babbage and went to his dinner parties. Now, later in life, Babbage experimented with sheet metal stamping and pressing for making gear wheels and similar parts. This was to deal with the problem he had of producing thousands of parts for his engines. Later, he adopted pressure die casting for making parts. It was newly invented at that time and didn't see extensive commercial use until the end of the 19th century. Babbage built many experimental models of mechanisms using these new techniques. And at the time of his death in 1871, a model of a simple mill and printing mechanism was near completion. His son, Henry Provost Babbage, took over his work. Babbage had bequeathed his drawings, workshop, and the surviving physical relics of the engines to Henry, who tried to continue his Babbage bequeathed his drawings, workshop, and the surviving physical relics of the engines to Henry, who tried to continue his father's work and to publish the engines after Babbage's death. He continued diligently with his father's. He continued diligently, and in 1888, Henry demonstrated a section of the mill of the analytical engine working to 29 digits, including the anticipatory carry-mate device. Then Henry built an experimental four-function calculator for the mill, completing it in 1910. Stephen Wolfer, a mathematician, wrote, "We may consider the engine as the material and mechanical representative of analysis, and that our actual working powers in this department of human study will be enabled more effectually than heretofore to keep pace with our theoretical knowledge of its principles and laws. Through the complete control which the engine gives us over the executive manipulation of algebraic and numerical symbols." Here's a picture, I think this is of Henry's model of the memory store. And you see the back of it here with the racks. And the front bottom here, I took these photographs because I wanted to prove to myself that I shouldn't be doing all of this mechanically, and I should be using a little servo motor to raise and lower all the bits to make it work in my model, that is. I thought it would be interesting to see where the analytical engine fell on Moore's law. Moore, as you most likely know, was engineer at Intel, and in the 1960s, he demonstrated that the number of chips, or circuits or transistors, doubles every 2 years. And the Babbage engine, I found this one on the web, didn't have to do it myself. There it is, the bottom left. The analytical engine is right there with Moore's law. Now it does show up 1900. If Babbage had actually built the thing earlier, it would be a bit to the left, but it still falls in the band of Moore's law. Next week, we're going to talk about modern computers, how they evolved, and Babbage and Ada Lovelace's legacy.